The surprising truth about reusable heavy lift is that recovery is not the hard part. Lowering the delivered cost to orbit depends on everything after recovery, especially inspection, refurbishment, and cadence. A large launch vehicle only becomes cheaper when it behaves like an operational asset. That means it can be recovered, checked, repaired when needed, and flown again. You also have to do this without giving away payload performance or taking reliability risks you cannot justify. Reusability is a system, not a trick. As of 2026, heavy lift with full reusability is still in a developmental regime. The most visible example is SpaceX Starship, documented in 2023 as still in early integrated flight testing. That matters because testing is where unknown failure modes show up. Developmental failures are not proof of futility, but they are proof of immaturity. For strategy leaders, that is the key distinction. You are not buying a commodity service yet. You are buying exposure to a capability curve. One reason cost claims stay slippery is that true marginal cost is hard to observe. You can price a launch contract, but that is not the same thing. The full recurring cost should include refurbishment labor, inspection depth, pad operations, insurance, and depreciation across the fleet. It should also include the operational overhead around propellant handling and range access. Yet audited 2026 numbers for heavy lift, fully burdened dollars per kilogram, are not provided here. That gap is not a footnote. It is a central risk in planning. So the first high-impact finding is about measurement, not hardware. If you cannot separate fixed development cost from recurring operating cost, you cannot see the real curve. If you cannot separate production of a new stage from the refurbishment of an old one, you cannot compare architectures fairly. In other infrastructure sectors, this would be basic accounting. In reusable heavy lift, it becomes a competitive weapon and a procurement vulnerability. A second finding is that the field is not one design. It is three big architecture classes. One path is partially reusable heavy lift. Another is fully reusable two-stage to orbit, often called TSTO. A third is reusable single-stage to orbit, or SSTO, which remains a high-stringency reference case. Partially reusable systems are attractive because they can preserve payload performance. You recover the most expensive elements, but you do not force the whole stack to come back. That can reduce the performance penalties of full recovery. It can also reduce operational complexity, depending on the design. Research has framed heavy lift economics explicitly around lowering recurring cost, not only achieving a first flight. That shift in framing is important. It turns rockets from bespoke projects into candidates for industrial operations. Fully reusable TSTO sits in the middle. Two stages give you architectural flexibility. You can optimize one stage for atmospheric return and another for vacuum performance. A fully reusable TSTO concept has been documented in published conceptual design work, reinforcing it as a serious design class. The strategic implication is that full reuse does not mean one vehicle. It can mean an operationally modular system. SSTO, by contrast, is the boundary line. Studies going back to the early 1990s formalized requirements in terms of mass fraction, thrust to weight, and engine performance. Work in the mid-1990s looked at advanced propulsion for reusable ballistic SSTO concepts, including reference architectures like Beta and Delta Clipper. The lesson is not nostalgia. The lesson is constraint. SSTO forces you to respect the rocket equation and re-entry heating simultaneously. Unless propulsion and structures improve enough, SSTO remains more useful as a feasibility yardstick than a near-term winner. A third finding is that recovery methods are still a wide design space. Propulsive return is only one option. Winged return elements have a documented research lineage, including the Baikal winged rocket unit concept for partially reusable super heavy systems. Mid-air capture has also been reviewed as a recovery concept, with modern synthesis work as recently as 2024. But here's the catch. The available evidence does not support ranking these methods by operational maturity, life cycle cost, or turnaround advantage. In other words, you can debate them, but you cannot yet score them confidently. For decision makers, that means do not overfit strategy to a favorite recovery maneuver. The dominant cost drivers may sit elsewhere, like inspection time, repair variability, or range scheduling. That leads to a fourth finding, and it is the one most people underestimate. Turnaround time is a mechanics problem, not a slogan. What dominates the reflight interval could be thermal protection inspection. It could be engine inspection. It could be stage transport back to the integration site. It could be the integration flow itself, or range availability, or payload processing constraints. Even anomaly review can dominate, because one odd sensor trace can ground a fleet until proven benign. High cadence is where fixed costs get amortized and where reusability pays off. Yet airline-like turnaround for heavy lift is not established here as a demonstrated condition. Treat it as a target. That distinction protects your forecasts from wishful extrapolation. A fifth finding is about reliability, and it has a different shape under reuse. Reliability models can lean heavily on build consistency and flight history across identical vehicles. With reusable stages, you now have an evolving asset. It experiences wear, refurbishment, inspections, and repair cycles. The key question becomes how many reflights and inspections do you need before reliability is empirically defensible? Until then, reliability estimates are partly first principles and partly small sample inference. Fleet grounding after anomalies becomes a major systemic risk. One incident can pause the whole cadence, and cadence is the economic engine. Now zoom out to demand, because even perfect vehicles do not guarantee the new economy. Lower cost and higher cadence can create new demand, but only past certain thresholds. If costs fall modestly, you might simply make existing missions cheaper. If costs fall far enough, you can unlock whole new categories, like frequent replenishment, larger in-space assemblies, or routine propellant delivery for depots. Demand-side elasticity becomes strategic. It tells you whether you are building capacity for a bigger market or just competing in the old one. Even if demand expands, coordination can become the ceiling. After vehicle recovery is solved, the bottleneck may shift to pad throughput, or it may shift to licensing and environmental review timelines. Range safety, debris governance, and orbital traffic management can all become the limiting factor. In that world, cost reduction does not automatically translate to access. It can translate into congestion. Over longer horizons, reusable heavy lift becomes a potential trunk logistics layer. In the near band from 2026 to 2050, the decisive question is whether recovery, inspection, refurbishment, and reflight can become predictable operations. In the mid-band from 2050 to 2100, validated recurring cost reductions could support cislunar infrastructure, propellant depots, and in-space assembly at industrial scale. Later still, rockets may face competition from non-rocket access systems for bulk cargo, like tethers or elevator-class approaches. Even then, reusable rockets could remain valuable for flexible launch, emergencies, and high-energy missions. So what should a senior allocator do with all of this? The most leveraged move is to demand comparability and auditability. Require reusable flight metrics that can be compared across providers. Track flight number per stage, refurbishment hours, reflight interval, recovery failure rate, and the real causes of launch delays. Most importantly, insist on a clear accounting structure for all-in recurring cost, not just advertised price. When cost transparency improves, strategy improves. Until then, treat reusable heavy lift as a promising, compounding frontier, whose true curve is still being measured. If you remember one line, remember this. Reusable heavy lift is not a vehicle story. It is an operations and evidence story, and the winners will be the ones who can prove it.